Hello everyone. Today we are going to discuss ray optics, some of the portion of ray optics. Mainly we are going to discuss that the focal length of a spherical mirror is half of the radius of curvature. So first of all, I start with some of the basic things which we have already discussed in the previous classes. See, we have actually considered two types of mirror. One is the convex mirror and other is the concave mirror. Now, out of these two types of mirrors, we have discussed that what is principal axis, then we have discussed the principal focus, then focal plane. We have also discussed that how incident light rays which are parallel and close to the principal axis meet after reflection from the concave reflecting surface. Okay. Now these things we have discussed for concave mirror. Same is the case with convex mirror also. Like if we consider a convex mirror here, then in case of convex mirror, again the same thing, we will consider a principal axis which passes through the pole here, and if we consider parallel light rays which are parallel to the principal axis, then if we draw a normal here, obviously the normal will pass through the center of curvature. The light ray will be reflected in such a way, it appears to be meeting the principal axis at a point which we consider as the principal focus. So principal focus of a convex mirror or convex reflecting surface may be defined as the point on the principal axis where the light rays which are initially close and parallel to the principal axis appears to meet after reflection from the convex reflecting surface. So I hope this is clear. Now one thing you need to remember, that the distance between pole and focus is known as focal length. Like in the concave mirror, this is the distance, and here in the convex mirror, this is the distance. This distance is known as focal length given by F. And the distance between the pole and the center of curvature, suppose here is the center of curvature C, so that is known as radius of curvature. We can show here this R. It is known as radius of curvature. Now what we are going to do here is we are going to prove that F is, that is the focal length is half of the radius of curvature. Okay. So let us see how it can be done. We take a new page here, and the topic is here we are going to actually prove that F is equal to R by 2. That is, focal length is half of the radius of curvature. I think it is clear to you. We are going to actually prove that the focal length is half of the radius of curvature, first for the concave mirror and then for the convex mirror. So let us see how it can be done. We start with the concave mirror. For a concave mirror, see, when we consider a concave mirror, let this be the concave mirror. This is the silvered surface, and let this be the principal axis. With the pole, let us consider an incident light ray which is close to the principal axis and parallel to it. From here, if we draw a normal, obviously we know that the normal passes through the center of curvature given by C. Now we will have a reflected light ray. This is the reflected light ray which passes through a point on the principal axis, which is known as principal focus, given by f. Okay, so here the focal length is represented by pf, which is given by small f, and the radius of curvature, which is pc, given by capital R. Now here you see, let us give some name here, m, n. Now we see here the incident light ray Mn. This angle which it makes with the normal is the angle of incidence, and this angle which the reflected ray makes with the normal is the angle of reflection. So here we can say that angle M and C is equal to angle F and C. The reason being, angle of incidence is equal to angle of reflection, that we know. Okay. Now this angle of incidence is equal to the angle of reflection. Further, this angle of incidence is also equal to this angle, alternate interior angle. So we can also write here angle M and C is equal to angle F C N. We can write here it is alternate interior angle. So therefore we can write angle F and C is equal to angle FCN. F and C and FCN are equal, so they are opposite sides. These are the opposite sides. They will be equal, so we can write here CF is equal to NF. The reason being, sides opposite to equal angles are equal. So therefore we have written this. Now see, the incident light ray is considered to be very close to the principal axis. So if it is very close, then NF is almost equal to PF. So we can also write NF to be almost equal to PF. The reason being, the incident light ray is close to the principal axis. So incident light ray is close to the principal axis, so therefore we can add on here, we can see here that NF is equal to PF, and earlier in the equation it is written as CF is equal to NF, so therefore we can write here CF to be equal to PF. Now CF is equal to PF, if we write here, then CF can be written as PC minus PF, which is equal to PF. So the equation here finally can be written as PC is equal to 2PF, where PC is the radius of curvature given by R and PF is the focal length. So finally, therefore we have an equation here, that is F is equal to R by 2. That is, focal length is half of the radius of curvature. I hope this is very clear to you. So if this is clear, the same kind of relation we can derive for convex mirror also. So let us quickly see how we can do that for a convex mirror. So second point we are going to discuss here for a convex mirror. So for a convex mirror, you see here, we first consider a convex mirror. We draw it. The convex mirror we have drawn. This is the principal axis. We consider an incident light ray. We draw a normal here. Which passes through the center of curvature. Then we have the reflected light ray here, which appears to be coming out of the focus here. Now you can see here, this is angle of incidence, which is equal to angle of reflection. This angle of reflection is equal to this angle, vertically opposite angle, and this angle of incidence is equal to this angle, which is corresponding angles. So the opposite sides, they are equal. Now let us give some name here. Say let this be M, this is N. So let this be R, S. Any names we can give. So this is pole also, which we can mention here. So here we can write that angle SNR, here we are writing this, angle SNR is equal to angle MNR. Reason being, angle of incidence is equal to angle of reflection. Also, angle SNR is equal to angle FNC, vertically opposite angle. Okay, now therefore we can write one more condition we will consider here, that angle M and R, angle M and R is equal to angle FCN, corresponding angle. So we can see here from the first equation, S and R and angle M and R can be written in the second and the third equation. Therefore we can hence write angle F and C is equal to angle FCN. So if these two angles are equal, their opposite side, that is CF, is equal to NF. The reason being, sides opposite to equal angles are equal. So if we write this, so we can say that since incident light ray is very close to the principal axis, therefore we can write NF to be almost equal to PF. So therefore, if NF is equal to PF, we can write CF is equal to, for NF we can write PF, and the value of CF is PC minus PF is equal to PF, and finally therefore we can write PC is equal to 2PF, which means PC is the radius of curvature, which is equal to twice of focal length. So the final result that we are getting here is F is equal to R upon 2. This is a value which we are getting both for concave as well as convex mirror. So I hope this is very clear to you. Any doubt, you can post me the doubt. Thanks.